Right, hello and welcome to a video and some notes on chapter 4.2, linear approximations and differentials. All right, so we've already discussed in our most recent project, I guess maybe not the most recent, we already discussed linear approximations in general, how we can use the tangent line to a function to approximate a function. Okay, so we did this with square roots. We know like the square root of 81 is 9. And that's nice and easy. But to approximate the square root of 79, just a little bit under 81, I know the answer is just a little bit under 9, but without an actual calculator, this is really hard to figure out. All right, so the general idea is that tangent lines can do a decent job of approximating these things. Okay, so we do the following. To create a tangent line to f of x as the square root of x, we have to find the derivative. All right, remember the square root is the 1/2 power. So we have 1/2 x to the negative 1/2, or 1/2 squared of x. All right, we can do that. That's a derivative. All right, we can then make the tangent line at x equals 81. Okay, so y minus the y value equals m x minus the x value, and the m, the slope, comes from our derivative. So the derivative, the slope at 81, that would be 1/2 times 9, 1/18. All right, so we have this. That's great. So now we want to find, I guess we can rearrange this. We could simplify it a little bit. I'm not going to simplify this too much. I don't think. Actually, the 81 and the 18 will reduce. 1/18x minus 81 divided by 18. 4.5. That's pretty good. 9/2, but then I have to add the 9 to it. So 27/2. All right, yeah, that's not a terrible fraction. We can work with that. All right, so the idea now is that I want to approximate our value. Actually, I'm going to go back. I have decided to change up my mindset here. Let's just add the 9 to the other side. 1/18 x minus 81 plus 9. We'll just move the 9 over. It'll make more sense in just a second. All right, so the idea of these linear approximations is that as long as I pick a number close to 81, I should have a pretty decent approximation of what the square root of that number is. Okay, so if we want to approximate the square root of 79, all I have to do is put 79 right here. All right, so 79 minus 81, like we can do pretty much all this in our head. That's -2. -2 times 1/18, that's -2/18, so -1/9 plus 9. All right, so that's what? 81/9 minus 9, so 80/9. All right, as a decimal number, if we wanted to, we could divide those two things. All right. And for calculators, we would have to divide those two things by hand, and we get 80 or 8.88888888. Great. All right, so the true question, the square root of 79 is 8.88819. All right, so this linear approximation, something that we could get simply by just dividing 80 by 9, all right, we have to do some work to get there, is correct for the first 3 decimal places. All right, that is pretty fantastic. Okay, so if we didn't have a graphing calculator, if we didn't have this type of technology, this would be a wonderful answer. I mean, we're correct to 4 significant values. I mean, that's huge. Okay, being that accurate is very impressive. Okay, given the situation. Okay? And so pre-calculators, pre-electronics in this way this was great for us. We use this constantly to be able to evaluate these tough numbers. All right, so let's try it again. We have sine of x, all right, and we know sine, or I guess pi over 6, 30 degrees. So we know that sine at 30 degrees, sine at pi over 6, we know that y value sine of pi over 6 is 1/2. Okay, so we can use this to approximate sine at 32 degrees, all right, which as a decimal number in radians is 0.5585. Now, whenever you do derivatives, integrals, when we get there, whenever you do these things with sine, cosine, tangent, you have to be in radian mode. Okay, these don't work in degree mode. You have to be in radian mode. Okay, so we have to do the derivative here. Derivative of sine, that's cosine of x. All right, and f prime at pi over 6. What's the cosine at pi over 6? Well, we should know that is the square root of 3 over 2. All right, so we can make a linear equation to approximate sine at pi over 6. Y minus 1/2 equals the square root of 3 over 2 x minus pi over 6. All right, so we have y equals square root of 3 over 2 x minus. Now pi over 6 as a decimal. Let's work in that world. Something like 0.5236. All right, so the idea for linear approximations is that we can take this number, put it in here for our x value, all right, forgot to add my 1/2. All right, and we can see what we got. So the square root of 3 over 2. This makes a little bit less sense because we're typing in square roots, but all right, so we have an approximation of 0.53. Okay, and if we actually do sine of, I'm in radians, 0.5585, we get 0.5299, all right, which very easily rounds to 0.53. All right, we're talking about being off in these two numbers by what, 3/10,000ths. Okay, so we are very accurate for this. Granted, we did have to use a square root of 3 in our calculations. All right, but we could approximate the square root of 3 like we approximated the square root of 79. Okay, so in general, these things allowed us to really be able to approximate sines, cosines, square roots of values that we didn't really know and didn't have a good knowledge of or a way to calculate. All right, so it allowed us a chance to find these things in just a slightly different way. All right, and if we use sine of x equals sine of x equals 0, 0 radians, 0 degrees, we can use that to approximate a few other things as well. So we already have f prime of x is cosine. We should know that when x is 0, sine of 0 is 0. So we have the coordinate 0, 0. All right, and cosine at 0 is 1. Okay, so we have a slope of 1 here. So our equation would be y minus 0 equals 1, x minus 0, which becomes just y equals x. All right, and so the joke, there's always, there's a joke between mathematicians and engineers. Engineers, they use math constantly, but a lot of them don't really know what's going on with math. They just know how to use it. And so the joke is a lot of engineers say that sine of x is just equal to x because of this. Okay, this linear approximation, sine of x is approximated by just x. Okay, and so we can approximate sine of 36, sine of 5 pi over, sine of pi over 36 by just calling it pi over 36. Those two things are pretty darn close, okay? And so that's kind of the joke. Like sine of 0 is 0. That's great. Sine of 0.1 is 0.0998. It's pretty close to 0.1. Sine of 0.2, for instance, is 0.1986. Okay, so the general idea is that with sine, for small values, the number you plug into sine is pretty much the same thing that you're going to get out of sine. Okay, once you get up to a little bit larger of your answers here, so for instance, sine of pi over 4, so 0.7. Now we're starting to get a pretty decent separation of these two things. But at the beginning, sine of x is really, really close to x for a lot of things. Okay. All right, so great. Linear approximations, I hope that we are okay with that. Make a tangent line, and then plug in a number really close to where you made your tangent line, and you should get a really close answer to it. Okay. Now, this leads to kind of the next general idea, this thing called a differential and a delta. All right, so this idea is kind of talking about with those linear approximations. When you have your number, so we were talking about, for instance, this first one I hope makes a lot of sense, around 81, all right, x equals 81. As long as you choose a number close to 81, we can pretty easily calculate the matching y value, all right, and how far that y value is going to be from the y value that we have, okay, and so that's what these differentials and deltas do. Okay, a differential is going to be like the dy, the dx. Okay, those come from the Leibniz notation, dy dx. Okay, and they represent very, very small changes to x and very, very small changes to y. As you make a small change to x, it should produce some small change in your y values. All right, deltas, as we get to these, are exact measures. Okay, so you're plugging in exact values, you're getting back exact values. Differentials are going to rely on the derivative, and so they give approximations. Okay, so here's the general idea. If we have y is f of x, and you take the derivative, that would be a dy dx, is f prime. You can kind of sort of multiply this dx to the other side, and so dy is equal to f prime of x times dx. Okay. So if you make a small change to an x value, a delta x, a dx I should say, and you know the x value, and you plug that into your derivative, it'll tell you how far you're going to approximately change your y values. Okay, so if we have y equals x squared plus 2x, and you take the derivative, okay, you can then kind of move this dx to the other side. Dy is 2x plus 2 times dx. Okay, and so if you're at 3, you can put 3 there, and you move just 0.1 away from 3, all right, you change your x value by just like a 0.1. How should that change your y value? Okay, we're at 3. We move 0.1 away from 3. So how should our y value change? Well, our y value should change dy. 2 times 3, that's 6, plus 2, that's 8, times 0.1. So our y value should change by about 0.8. A 0.1 change to our x is going to make about a 0.8 change to our y. All right. Now these are approximate. All right. They're like the linear approximations that we just dealt with. We used a derivative, so we have this like approximation. So a 0.1 change to our x produces a 0.8 change to our y when x is 3. All right, that's called a differential. A delta is exact. Okay, so a delta y is equal to, when you plug in your 3 would be like your a, and your 0.1 is there. So we want to do 3 plus 0.1 squared plus 2 times 3, that's 3.1. We can just type that. All right, so if we plug in 3.1, we're at 3 and we move 0.1 away. All right, and then we plug in just 3. How far measured apart are they? All right, so deltas are exact. They're not approximations. These things are exact. DYs, differentials, are approximations. Deltas are exact. All right, so what I mean, if we just plug in 3.1, all right, our function is at a height of 15.81. If we plug in 3, we're at 15. All right, 15.1, take away 15. Point. I didn't do that right, didn't type that in right, but it's 0.81. All right, so a delta is the exact difference between a function, and when you move that function. All right, so the exact distance is 0.81. Our differential that we calculated using approximation was 0.8. Now, usually these two things should be very, very, very close. One of them is a little bit easier to calculate. One of them is a little bit harder to calculate. I'll let you guess which one's easier and which one's harder. 3, 2, 1. Yeah, the differential is very easy to calculate. You take a derivative. We can do that really easy. We plug stuff in. All right. The deltas are a lot more time sensitive, and we have to do a lot more. Okay. Our differentials, we just kind of have to plug in a couple things, and it goes quick. Okay. So we can use these things to calculate error. All right, and that's fun. All right, so let's say we have the volume of a ball and the volume of a sphere, 4/3 pi r cubed. If we must physically measure the radius, we're not always going to be accurate. All right, when you actually have to measure things, all right, there is human error. There is error by means of, is it exactly at 5 centimeters, or is it at like a 5.1? When do you go to millimeters? How accurate can we truly be? Okay, so we have this thing. Let's say that we can be accurate within 0.1 centimeters. Okay, so let's calculate our differential dV. All right, well, dV is the derivative with respect to r. So if we take this derivative, 4/3 pi times 3 r squared, the 3's will cancel, so we've got 4 pi r squared. If we get the dV by itself, we're here. Great. All right, so we now know the radius is 5, and our dr, how much accuracy we have, is 0.1. So 4 pi times 5 squared times 0.1. All right, so our differential, our dV, is 31.4. All right, so by being just 0.1 centimeters off, all right, when we're measuring, we can have an error to our volume all the way up at 31. All right? We could be off by 31 cubic centimeters based on just a 0.1 error in our measurement system. So that's a pretty big differential, okay? So let's calculate our delta, how much we truly are off if this is the situation, okay? So our delta, we do, if our if our delta R is 0.1, our delta would be, our radius was 5, so 4/3 pi times 5.1 cubed minus 4/3 pi times 5 cubed. All right, so if we over approximate our radius by 0.1 and we subtract these two values, it means our true volume would be off by 32.048. Okay, so our differential said we might be off by about 31.4. If we truly were 0.1 off in our radius, the math truly says that we would actually be off by 32 centimeters cubed. Okay, so being off by an increase of 0.1, we're off by 32 instead of the 31.4 that we approximated. But the idea is that with differentials, we could be increased by 0.1 or decreased by 0.1. So if we also did this with our 4.9 for radius, we would be all the way down here at 492. We don't have to recalculate that one. All right, and so if we under approximate our radius, we're going to be off by 30.79. All right, so notice how 31.4 is kind of in between these two. All right, we were a little below this approximation, but a little bit above this approximation. All right, so differentials are going to kind of cut the middle, where these deltas are going to be very exact. All right, and they're usually not going to be the same answer. We don't need to worry about the plus minus with our differential, because it's just going to be, plus minus here, plus minus there, where our deltas, the true exact measures, might not be the same difference, all right, depending on if you over approximate or under approximate. All right. Last but not least, we have this thing called a relative error. All right, so the relative error is when you take your differential and you divide by the true exact value, all right, and then you times by 100. So our dV, our differential, was 31.4. 16. We divide that by the true volume of our sphere here, which we found was 523.598, and then we times by 100. All right, and so it just kind of relates this being off by 31 to a percentage number, which is nice. Being off by 31 seems like a lot, but when you talk about the volume of this entire sphere is in the 500s, being off by 31 just means that we're off by about 6%. All right, if we have an error measurement of 1.1 centimeters, it means that our volume is going to be off by about 6%, which is pretty significant when you're talking about a radius of 5 centimeters, and that's a pretty good accuracy rate, but it could produce a 6% overall error to our problem. And so being accurate in your measurements is really important. Imagine a 0.1 centimeter error for your measurement would give you a pretty good overall, but gosh, that's pretty large there. Okay. All right, so let's just try a couple more. Make sure that we're good with this. All right, so a cardboard box is a cube. It should measure 3 feet on all sides. All right, and we have a potential error of 1 inch as we're measuring. Now, first thing I notice is that 3 feet and 1 inch, we need to make these two things the same unit. So I'm going to go ahead and cross this out and put 36 inches. Okay. So find the differential dV of the volume and the relative error of the volume. Well, we're talking about the volume. So the volume of a cube is just s cubed. So our dV/ds would be 3s squared. So our dV is 3s squared ds. All right, we think that we have a side length of 36 inches, but we might be off. Our ds is an error of 1 inch. So our ds is 1. So our differential, our dV, is 3,888 inches cubed. That is a huge potential differential, right? But what's that in relative terms, right? So our relative error, you take this differential, you divide by the true volume, and you times by 100. So we're potentially off by almost 4,000 cubic inches, but the true volume is in the 46,000, meaning our total error is about 8%. Okay, there we go. So find the differential of the surface area and the relative error of the surface area. All right, the surface area of a cube is just the area of all of these surfaces. Now I know that's s and that's s, so each side would be s squared. And there are 6 sides. All right, so our differential dA/ds would be what? 12s. So dA would be 12s ds. Now we know that the side length is supposed to be 36 inches. And we think our ds, how much we might be off of, is 1 inch. So 12 times 36 times 1. We might have an error of around 432 square inches. Now, what is that in terms of our relative error? Well, we take that 432 and we divide by the approximate area. So 6 times 36 squared. So 7,706. We times that by 100 to make it a percentage. So only about a 5.5% error. 5.6, let's be a little bit better on our rounding. All right, so our surface area will be a little bit better compared to our volume. Okay. And so differentials are, I hope you agree, are very quick and easy to calculate. All right, you take your derivative and then you plug some stuff in. The deltas, the exact measures, are usually a little bit more intensive. Okay. All right. A circle, radius of 10, drawn with a compass, traced by hand with a marker. Tip of the marker is a 1/4 inch wide. All right? So we're talking about the circumference of a circle. So 2 pi r would be the circumference. So the derivative here, dc dr, would just be 2 pi. So our differential for the circumference would be 2 pi times dr. Okay, now our dr, our differential here would be 0.25 inches. Everything's in inches. So 2 pi times 0.25. So we might be off by about 1.57 inches. Just a quarter of an inch width additional on our circumference might add a total circumference of 1.5 inches. That's pretty significant. But we take our 1.5 and we divide that by the actual circumference of our circle, which should be 2 pi times 10. We then times by 100 to turn that into a percentage. So even though it might be off by 1.5 inches, that's only a 2.5% relative error. All right, so not that big of a deal. All right, to find the differential and relative area of the traced circle. All right, well, the area of a circle, pi r squared. Derivative there would be 2 pi r. So our differential for the area would be 2 pi r dr. Now we know the radius is 10 and our error on the radius is 0.25. So our error differential, 2 pi times 10 times 0.25, means we have about a 15.7 square inch area differential. Okay, relatively though, we take our 15.7, we divide that by pi times r squared, and then we times by 100. So only about a 5% potential error. All right, but that is kind of crazy when you think about it. Being off by just a quarter of an inch on your circle might produce even a 5% error on this 10-inch radius circle. Okay, so that just kind of, I hope, ties into the idea that being accurate in measurements in the real world can produce some very wildly different results. A small error in measure can produce very large errors in observed values. Okay. All right, so that's it on linear approximations and differentials. Go ahead and try the 4.2 My Open Math, and good luck.